Hi everyone, happy Friday. In today's video, we're going to be discussing sigmoid function and we're going to be talking about the following points in relation to sigmoid function. Its mathematical intuition, derivative of sigmoid, graphical intuition, advantages of using sigmoid function, disadvantages of using sigmoid function, use cases like where is it used, and Python implementation. If you're new here, then I am Radhika. This is my YouTube channel Datazard. If you have not subscribed already, then please do consider subscribing as I don't want you to miss out on any future videos. And now without further ado, let's get started. Now let us try to understand this mathematically. So formula for sigmoid function is equal to sigma of x. This is how we denote sigmoid function, is equal to 1 upon 1 plus e to the power minus x, where this e is Euler's number, which is equal to 2.718, and this x is input. So whatever input we give, we will get the output by plugging that input in this function. Now let us try to take some values of x and plug those in here. So first I'm going to take x is equal to 2. So when x is equal to 2, we'll find sigma of 2 will be equal to 1 upon 1 plus e to the power minus 2. That will be equal to 1 upon 1 plus 2.718, that's value of e to the power 2. And I've already done the calculation, so this comes out to be 0.135. So this comes out to 1 upon 1.135, that is equal to 0.88, which is close to 1. Now let us take another value of x. This time I'm going to take it as a negative number. So x is equal to minus 2. For this, let us again try to calculate sigma of minus 2, which is equal to 1 upon 1 plus e to the power minus of minus 2, that is equal to 1 upon 1 plus e to the power 2. I'm going to plug in the value of e, 1 upon 2.718 to the power 2, which is equal to 1 upon 1 plus 7.389, which is equal to 1 upon 8.389, which comes down to 0.11. That is, this is close to 0. Now let us take last value of x. That value would be equal to x is equal to 0. Let's try to use this. So now we have to find sigma of 0, which is equal to 1 upon 1 plus e to the power 0, which is equal to 1 upon 1 plus 1, because anything to the power 0 is 1. That is equal to 1 by 2, which is equal to 0.5. So when it is 0, then it is 0.5. When it is a negative value, when x is a negative value, then we are getting value close to 0. And when x is a positive value, then we are getting a value which is close to 1. The range of sigmoid function is between 0 and 1, both included. And domain of sigmoid function is from minus infinity to plus infinity. What is range? Range is what would be the output. If we try to give any value of x, what would be the output? So output will always be between 0 and 1. And domain means what input values can this function take. So it can take any value from minus infinity to plus infinity. That is, x can be between minus infinity to plus infinity, any value, and the output of that would always be between 0 and 1. So we can say that this sigmoid function is squashing the input in range between 0 and 1, both included. Now because it is squashing this input in this range, such functions are also called as saturating functions. What are saturating functions? Those functions whose output lies within a certain range are called as saturating functions. And you know that sigmoid function always is between 0 and 1. That's why it is a saturating function. Non-saturating function would be one that is not having any defined range. But sigmoid is a saturating function. Now there is another property of sigmoid function which is called as monotonicity. Sigmoid function is a monotonically increasing function. Now you would be thinking, what is a monotonic function? So monotonic functions are those functions that move only in one direction. They are moving only in a single direction. They are either always increasing or always decreasing. And sigmoid function falls in first category. When the function is always increasing, it is called as monotonically increasing function. And when the function is always decreasing, it is called as monotonically decreasing function. So any function that moves in one direction is called as monotonic function, and our sigmoid function is type of a monotonically increasing function. Now you would think, how can they define this mathematically? So we can say that for two values of x1 and x2, where x1 is less than x2, when we plug in these values of x1 and x2 in the function, then f of x1 should always be less than or equal to f of x2. That's when we will say that it is monotonically increasing function, because as the value of x increases, this is also increasing. Next question would be, how to check if a function is monotonically increasing? And the best way to do this is using a derivative. So derivative of sigmoid function is actually equal to sigmoid function multiplied by 1 minus sigmoid function. This is the formula of derivative of sigmoid function. Now, when we plug in any value of x, we will find that this slope of sigmoid function, because derivative is also called as slope, so this slope of sigmoid function will always be a positive value, and because it is always a positive value, we say that it is monotonically increasing function. So when the derivative is always positive, then it is called as a monotonically increasing function, and that is true for sigmoid function. That's why we say it is monotonically increasing. Now, if you look at this carefully, we know that sigma of x can only be between 0 and 1. Let's try to find these values when sigma of x is equal to 0. In this case, sigma dash of x, which is this derivative, will be equal to 0 multiplied by 1 minus 0. That will be equal to 0. Let's try to plug in a different value when sigma of x is equal to 1, because that's the only other extreme. So sigma of x would be equal to 1 multiplied by 1 minus 1, which will again be equal to 0. For any other value also, this will be a positive number, and that's why we say that because derivative is coming as a positive number or 0 always, that is why sigmoid function is a monotonically increasing function. Now there are a few other properties of sigmoid function, and the next one in the list is it is continuous everywhere. Because it is continuous everywhere, it is also differentiable at all points. Now this is a very important property for an activation function, that it should be differentiable at all points. Now you would think why? The reason is because when we are doing back propagation to update the weights and biases in the neural network, at that time we have to find the derivative of activation function because of chain rule. So that is why it is super important that the activation function that we choose is differentiable so that we can easily do these types of calculations. So sigmoid function is differentiable, so this is a good function to be used as an activation function. Now let us try to understand this scenario. So I'm going to create a neural network with two inputs, one hidden layer and one output layer. Now this input is x1 and x2 and it is connected to hidden layer neuron. Both of these are connected, and then this neuron is connected to the output layer neuron, and this is the output that we get by hat. Now both of these neurons, they have their own biases. I'm calling them B1 and B2, and I'm calling these weights as W11, W12, W21, and I'm calling the output from this neuron as O1 and output from this neuron as O2. Now when we have to update weights or biases, then the formula is W new is equal to W old minus eta, which is the learning rate, and then derivative of loss function with respect to W old. Now taking this W11 as an example, suppose that we had to update W11. In this case, what we need to do is we need to find W11 new, that will be equal to W11 old minus eta, derivative of loss function with respect to W11 old. Now let us try to focus on this part of the equation. This is the learning rate and this is the derivative. So we can write this as derivative of loss function with respect to W1 old will be equal to derivative of loss function. Now loss is dependent on the output of output layer, which is O2. So I'll write O2. Then this O2 is dependent on O1, and then this O1 is dependent on W11. So we will multiply this by derivative of O2 with respect to O1, and then derivative of O1 with respect to derivative of W11. That's how the chain rule works. We start from the end and propagate backwards. Now again, if we look here, we can write this O2 with, so the input to this neuron is O1, so O1 multiplied by weight, which is W21, plus bias to this neuron because there is no other input, and then on top of this we apply an activation function. So if we replace this value over here, so this would be derivative of this sigmoid function, which is O1 multiplied by W21 plus B1 divided by del of O1. So essentially what we are doing is finding derivative of sigmoid function, and because we are finding derivative of sigmoid function, this is going to happen for each of the hidden layers where we have activation function. That's why, because of chain rule, we have these kind of derivatives which are derivatives of the activation functions. Now let us talk about the graphical intuition of sigmoid function. So we know that this sigmoid function is 1 upon 1 plus e to the power minus x, and we know that it ranges between 0 and 1. So that's why the graph is like this. It is an S-shaped curve because you can see here an S shape is being formed, and we know that sigma dash x is derivative of sigmoid function, and always remember that the derivative of sigmoid function will be between 0 and 0.25, as you can see from the diagram here as well. So when x is equal to 0, then the derivative of sigmoid function will be equal to 0.25, and at all the other places it will follow this type of curve which is shown in blue color. Now if you look here, the value of this sigmoid function which is shown in green color is between 0 and 1. These are the only values that it can take. Positive values, they are closer to 1, and negative values from this side, they are closer to 0. So this is 1, 2, 3, 4. This side is -1, -2, -3, -4, like that. So always remember that sigma will fall between 0 and 1, whereas sigma dash x, which is derivative of sigmoid function, will fall between 0 and 0.25. Let us also talk about the property of sigmoid function, that it is monotonically increasing. So if you look here, as the value of x is increasing, our function value is either the same as the old one or it is increasing. There is nowhere on this curve you can see that the value is dipping at any point. So that is why visually also we can see that it is monotonically increasing function. It is always increasing. I forgot to mention another property of sigmoid function, which is called as being zero-centered. This function is not zero-centered. Now we first need to understand what zero-centered functions are. Those functions that give output which is distributed equally on positive and negative side, those functions, they are called as zero-centered function. Like if a function outputs something like -2, -1, 0, +1, +2, this function is a zero-centered function because it is outputting values in the negative scale as well as the positive scale. Whereas with sigma, we know that the values will always be between 0 and 1, which means it is only giving positive values. And because it is only giving positive values, we say that it is not a zero-centered function. We can see this from the graph as well. We only have values from 0 to 1. We don't have anything in the negative region. That's why it is not zero-centered function. Now let us talk about the advantages of sigmoid function. And the first advantage is that it is non-linear function. Why this is an advantage? Because in neural networks, we have to understand complex relationships. And these complex relationships, they are of non-linear nature. That is why it is important that our activation function is a non-linear function so that our neural network can capture these complex relationships. Second is, it is differentiable at all points. And I've already explained previously as to why this is an important value, because when we do backpropagation to update our weights and biases, then we have to find the derivative of the activation function because of chain rule. Now the output of this function is between 0 and 1. Because it is between 0 and 1, we can treat this function as a probability function. Why? Because its output is between 0 and 1 and probability is also between 0 and 1. So we can set a threshold like 0.5. So anything which is less than 0.5 is considered as 0 and anything greater than 0.5 will be considered as 1. So we can treat this as a probability function, and it is actually used in binary classification at the output layer so that it can tell the probability at the output whether it is a yes or no or spam or ham. So probability 0 or 1. Fourth is, it has a smooth gradient. So these were the advantages of sigmoid function. Now let us talk about the disadvantages of sigmoid function. The first disadvantage is that it causes vanishing gradient problem. Let us try to understand what this problem is. So suppose I'm taking the same example as we did previously. These are our two inputs. This is our hidden layer and this is our output layer. And we are trying to connect all of these inputs with these neurons. This is X1, this is X2. Output from this neuron is O1. Output from this neuron is O2, which is also called as Y hat. We have a bias here which is called as B1, and this neuron has a bias B2. And we have weights here. So weight is W1, this is W2, W3. Now suppose that we are trying to update this weight. So we know that the weight updation formula is W new is equal to W old minus learning rate, derivative of loss function with respect to W old. Now we are focusing on this term only because this is the most important term which will help us understand the vanishing gradient problem. When we try to evaluate this, let us try to do this for W1. So our formula would be W1 new is equal to W1 old minus eta, derivative of loss function with respect to derivative of W1 old. Now, expanding this term, we will have derivative of loss function with respect to W1 would be equal to, we can say that this derivative of loss is first dependent on O2 because we are going in backward direction. So we find derivative of O2. Then this O2 is dependent on O1. So we say derivative of O2 with respect to derivative of O1. And then again, this O1 is dependent on W1. So derivative of O1 with respect to derivative of W1. When we cancel these out, then we are left with the original thing. And this is what is chain rule. Now in this chain rule, suppose that we are evaluating this node now. So we know that O2 can be written as this O1 multiplied by W3. So O1 multiplied by W3 plus bias. So O1 multiplied by W3 because this is the input to this neuron whose output is O2, and then we add bias which is B2, and on top of this we apply the activation function because every neuron, it performs two operations: summation of the product of its input with the weight and then an activation function. So now if we replace this over here, we will get derivative of O2 with respect to derivative of O1 is equal to derivative of sigmoid function of O1 multiplied by W3 plus B2 and then derivative of O1. So if you look here, what we are doing exactly here is derivative of sigmoid function, and no matter what value of O1, W3 or B2 we have, this will always be between 0 and 0.25 because that's what the derivative of sigmoid function comes out to be. Because this is always between 0 and 0.25, suppose that instead of just one hidden layer, we had 100 hidden layers. So this would be, let's say for the first hidden layer it comes out to be 0.25, then for second one it is 0.01, then it is 0.001 and so on, which means this is coming out like this. This is a very small number. It's a very, very, very small number. Like it is 0.0000000 and a few more zeros and then 1. If we try to plug this in here, then this is a very small number. Eta is also a very small number because we have to choose a smaller learning rate. So when we subtract this old W with this very small number, there is hardly any difference. So W new will match what W old is, which means there isn't any update happening, which means our neural network is not learning. And this is what exactly is called as vanishing gradient problem. When we have multiple hidden layers like a deep neural network, and in all those hidden layers we have sigmoid as the activation function, then we end up with this kind of situation where we multiply the derivative of these sigmoids functions multiple times, which leads to a very small number. And when we plug that very small number over here, our W new is almost equal to W old, which causes vanishing gradient because our neural network is not learning. This exactly is what is called as vanishing gradient problem. Third disadvantage is that it is non-zero centered function. Why this is a disadvantage? Because it will only output positive values. Because it is only outputting positive values, we will have slow training process. It is not distributed equally around 0, which means it is not having positive and negative values. It just has these positive values. And because it just has positive values, the weight updates will be zigzag. And because of this zigzag updates, we will have slow training. Fourth is it is computationally expensive. Why? Because we have to calculate e to the power x. We have to calculate exponential here. So these were the 4 disadvantages of using sigmoid function. Next, let us discuss the use case as to when we can use sigmoid function. So we can use sigmoid function for activation function in the output layer, and this is especially useful when we are doing binary classification, because in binary classification we need output between 0 and 1 because that's what the probabilities are, and sigmoid function gives us this kind of output. That's why we will be using that in the output layer. Let us now try to implement sigmoid function using Python. So I'm going to use math library. So I'm going to do import math, and then I'm going to define function called as sigmoid, which can take input as x, and here we can just simply return the formula, which is 1 divided by 1 plus math.exp. That's why I'm using math library, so that directly we can use math.exp to find the exponential of x and close off the brackets. Now we know that this function will always return a value which is between 0 and 1 because we are implementing sigmoid function. So let's try to use this. So let's try to find sigmoid of 2 like we did with hand. It is 0.88, which matches the value that I found out. Then let's do sigmoid of -2. That will be equal to 0.11. Sigmoid of a big number, which is equal to 1. So we can see that all of these values, they are ranging from 0 to 1. We can also implement this using NumPy library. So if we don't want to use math, then we can do import NumPy and use NumPy's np.exp function. So we're going to use it in the same way. Sigmoid NumPy, I'm just going to call this function as sigmoid NumPy, which will take value as x, and it's going to return again the same thing, 1 divided by 1 plus, now this time instead of doing math.exp, we are going to do np.exp minus x. Now let's try to run this function. So I'm going to give it the same value. So let's give it 2. We have to set it as np, and now when I do it, I'm getting the same value as I got for math.exp. Then I'm going to call this for -2 like I did earlier, and this should give me 0.11. So this way we can either use math library or NumPy library to calculate sigmoid for any input. Thanks for watching. Did you find today's presentation helpful? Let me know in the comments. I would love to hear your feedback. I'll see you in my next one.